All right, everybody, this is going to be our last notes video for today, and if you are following along, you will notice that I skipped page 16. Page 16 is a really good review of a bunch of the tests that we've learned, but there's no new learning on page 16. So if you'd like to do that as part of your review for your assessments later this week, it is an excellent set of problems, but it's not necessarily something that we need to go through in terms of notes, which is why I've skipped over it. So we are here on page 17. We're going to take care of our final topic for Unit 10A, which is topic 10.9. And this is actually going to revisit some of what we've already talked about, and it's just going to kind of firm up or make our conclusions a little bit better, a little bit more specific, especially in terms of alternating series test and a couple of other kind of detail things. So the topic here is about the difference between absolute and conditional convergence. So what we're doing is we're trying to think about what type of convergence is happening in series where there are negative terms sometimes. So it doesn't have to officially be an alternating series. It doesn't have to be half positive terms, half negative terms, although we often use this idea when it comes to alternating series. But this more kind of generally applies to series that have at least some terms which are negative, and it considers whether the series would converge if the absolute value of all those terms was taken. That would be called absolute convergence. So basically it converges regardless of whether the terms are positive or negative. That's kind of a more powerful version of convergence. Or if it really only converges conditionally, so dependent on the fact that some of the terms are negative, okay? So you'll see the first theorem here is something we've already talked about. If the series, the absolute value of a sub n converges, then it means that your a sub n series converges as well. So basically, if you take the absolute value of all of your terms and you get a convergent series, then that means that your original series, even if it had some negative terms, will converge as well. The converse of this is not true. So just because a series converges doesn't mean the absolute value of the series will. So make sure you get this in the right order. If the absolute value of the series converges, then we know that the series converges, and we call it absolute convergence in that case. You'll see this down here. The series a sub n is absolutely convergent if its absolute values converge. However, we do have some series, the alternating harmonic series is an example of this, where if you take the absolute value of the terms, it would become a p-series with p equal to 1, and it would diverge. And so if you take the absolute value of the series and you get a divergent answer, we have to come back and consider whether the fact that half of the terms being negative or some of the terms being negative results in this series converging in what we call a conditional way. So based on the condition of negative terms showing up. So we'll say that a series is conditionally convergent if the series converges, but its absolute value diverges. And this is where we have to be really careful, because it will feel like when we're doing the test that we get the diverge answer first generally. We'll have to remember to come back and consider whether or not it can conditionally converge if we take into account those negative terms. Okay, I think the best thing to do is to just jump in and see it, because otherwise we can talk ourselves in circles. So for example 1, we have a series that definitely has some negative terms. In fact, it looks like it probably has alternating terms. They've listed some of them out for us. So we've got 0 factorial over 2 to the 0 minus 1 factorial over 2 to the first plus 2 factorial over 2 squared. So it looks like even terms or even powered terms, are going to have positive signs, and then odd powered terms are going to have negative signs. Okay. In either case, that means that we're dealing with something that has some negative terms. So what we want to do is we want to start out by considering the absolute value of this series. And so we're going to think about the series from n to infinity still, but of the absolute value of negative 1 to the n times n factorial over 2 to the n. that would be equal, if we think about what would happen when we apply those absolute values, it's going to take away that -1 alternating piece. So we'd be dealing with just n factorial over 2 to the n. And so what we're testing for first, some people think about this as like part 1, is absolute convergence. If this series converges, then we know that this series has absolute convergence. So it converges even if all of the terms are positive, which is a really important thing to know. However, if we think about this, maybe let's just use the nth term test. So I'm going to take the limit as n approaches infinity of n factorial over 2 to the n. Factorials grow at a much more rapid rate than exponentials do if we know what the base is. And so that is going to give us an infinite result. And so what we see is the absolute value of our series actually diverges by the nth term test, because this was not equal to 0, okay? Now you might think, we're done, but we're not. All we've figured out so far is that the absolute value of our series diverges. So it is still possible that our series itself, where some of the terms are negative, is going to converge. So once we've kind of shot for absolute convergence in part 1, we're going to come back, if we get a negative, a diverge situation, and we're going to see if we have some kind of conditional convergence. Now, because this is an alternating series, the best thing for us to do is to try to think about the alternating series test. We do have what we need in order to do the alternating series test. Remember, our requirement is that a sub n is greater than 0 if we remove the alternating piece, which we've got. So the first part of the alternating series test would be to take the limit as n approaches infinity of the positive part, the non-alternating part of the series. Well, you might be thinking, wait a minute, we already did that. You're right, we did already do that. We figured out that that was equal to infinity, which is not only bad news for absolute convergence, but it is also bad news for our alternating series test. That is supposed to be equal 0 for our alternating series test to end up with a convergent series. So now we have the evidence that we need between a combination of part 1 and part 2 work here to make our conclusion that the series, and sometimes when you kind of dealt with multiple different series, you might want to just go ahead and rewrite it for clarity's sake. So our original series from n equals 0 to infinity of -1 to the n factorial over 2 to the n diverges. It did not converge absolutely, and it did not converge conditionally because it failed the alternating series test. Okay? All right, let's look at part B and see if something different happens. So for part B, again, we have negative terms. This time they're showing up first and third in the lineup, but they're still there. So what we're going to do first in part 1 is we're going to think about the absolute value of this series. So the absolute value of -1 to the n root n is going to eliminate that absolute value, or not absolute value, sorry, that negative to the power. I'm going to rewrite this as a number at the same time. So that's going to be 1 over n to the 1/2. All right, let's think about that as a series. I'm really hopeful that you recognize that as a p series. P is equal to 1/2. When we're dealing with p series, we compare it to 1. 1/2 is less than 1, so that means that this is a divergent p series, because p equals 1/2, which is less than 1. Remember, it takes p greater than 1 for a p series to converge. So this, again, is part 1. That tells us it's not going to converge absolutely because the absolute value of our series diverged. So moving into part 2, we do have an alternating series, so we're going to think about the alternating series test. The first part of that alternating series test, after we've checked to make sure we've got 1 over root n, yep, that's going to be greater than 0. First part is to take the limit as n approaches infinity of just the positive part. So we remove that alternating component. So when I take this limit, sure enough, 1 divided by a very large number, square rooted, or to the 1/2 power, is going to approach 0. So we've met the condition of the first part of the alternating series test. The second part is to make sure that those terms are non-increasing. So this is where we took our values and we compared what happens when we go to the n+1 term. We need that to be less than or equal to the nth term. And that might be a little bit tricky for you to think about in this fraction and rational power format. So if we think about going ahead and cross multiplying, that would bring this n to the 1/2 up to the top over here. I'm going to rewrite that as root n. And we're going to compare that then to root n+1. And I think that's pretty clear. Root n is going to be less than or equal to root n+1 because this is more than this is. So we've met the second condition of our alternating series test. So our series didn't converge absolutely because the absolute value of it diverged. But when we took into consideration the fact that the terms alternate, positive, negative, it did converge. That means that the series converges conditionally. So back when we were in topic 10.7 and we got to the point where we were at the end of a problem and we had used alternating series test and made the conclusion that it converges, we were actually concluding conditional convergence. We just didn't realize it at that point in time because we hadn't talked about the difference between absolute convergence and conditional convergence. Okay, we've got one more example of this on this page. So let's go ahead and knock out part C here. Part C is not technically an alternating series. Sine x might be throwing you off a little bit, but sine x is just saying for all x values, you're going to take the sine value and you're going to raise it to n. N is your series operator, right? So n is the thing that's changing. It's going from 0 to 1 to 2 to 3 up to infinity. X can be any value. And so what we need to do here is we need to think about what's really true if we're talking about sine of any value. I'm hopeful that you all know your range for sine. We know that sine is always going to be between -1, less than or equal to sine x and +1. And so that does mean that for some values of x, we will have negative terms, because this input might be negative and then it might be raised to an odd power. So we do have a situation where there are negative terms. So if we're going to test for absolute convergence, we need to make sure that we show that we're considering the absolute value of this series. So we're going to write the absolute value of sine x to the n over n factorial. And then if we think about what that could really simplify to be, to give us a series that it's a little bit easier to investigate, -1 to 1, if we raise it to a power, is always going to end up being somewhere between -1 and 1. But if we take the absolute value of it, then we can kind of compare it to just being a +1 value. I'm a little bit hesitant to write this equals thing that I just wrote down because I feel like we're headed more towards a direct comparison test than anything else. So I'm going to clean this up just a little bit and get rid of this equal sign just so that I don't have things connected to each other that aren't truly equal. Let's just try to imagine instead, maybe not even a series. Sorry, guys. If we're going direct comparison, we're really just thinking about this input. So I'm going to make a statement here about sine x to the n over n factorial and its absolute value. I believe that that is always going to be either less than or equal to 1 over n factorial. Because if sine x is equal to -1, it will equal 1 over n factorial. If sine x is between -1 and 1, then when I raise it to a power, it's going to get smaller than 1, like 1/2 raised to a power will always be less than 1. And if it's equal to +1, again, it's going to be equal to 1 over n. So I think this absolute value will always be less than or equal to 1 over n factorial. So if we take a little comparison sidestep, let's see if we can figure out what's true for this as a series. The sum of n equals 0 to infinity of 1 over n factorial. I believe that this is also another little definition that we've seen before. Let me grab our table that we filled in the other day. Remember I mentioned that there were some series that you had worked with from your pre-calculus days? Yep, sure enough, here it is. So the sum from n equals 0 to infinity of 1 over n factorial is e again. So there's a couple different definitions or ways that we can talk about what e is equal to. We saw one in that previous example, and this is another one. And so if that series has a finite sum, we know it equals e, then that means that this series converges. It actually converges to e. We don't often know what it converges to, but we do in this case. We're not really using any of our tests. We're just using what you know from your pre-calculus days about this infinite series actually converging to the number e. Okay, so what does that mean? If this series converges to e, but it's bigger than our series, then by direct comparison, we know that our series converges. And we were considering the absolute value of our series, and so that tells us that our series converges absolutely. So I'm going to write the series in here again, just so that I'm being super clear about what I'm making a conclusion for. Our original series converges absolutely. Sorry, I kind of ran off the edge of the screen there. Again, that's true because a series larger than the absolute value of our series converges, which means we're using direct comparison. We probably want to say that as part of our evidence. Okay, so that's our first series that we've actually ended up with absolute convergence. We don't come back in and do part 2 with the alternating series test. Number 1, this isn't an alternating series, so we would have been in trouble. But number 2, if we get absolute convergence, then we don't have to come back and say whether or not it's conditionally convergent, because we already know that it's absolutely convergent. All right, we got a few more examples on page 18. I know this topic is a little bit longer than the others, so hang in there. Go ahead and flip to page 18, and we're going to finish it up. All right, on the top of page 18, there are a couple different visuals that are here to kind of help you organize your thinking. If we have a series, right, we can start by thinking about whether or not it diverges or converges. And if it converges, then we can try to be more specific about whether that convergence is absolute or conditional. That's helpful, but not really the way my brain works. My brain works more this way. It thinks it's easier to kind of test for absolute convergence first. That's what I've been modeling in the problems that I've been doing. And if we get absolute convergence, then we're just done, okay? But if we get a diverge answer when we're dealing with the absolute values, then we go back and we test for conditional convergence. So whichever approach you want to take is fine, but this is the one that I've been using. It's just the one that makes more sense to my brain. All right, example 2, let's see what they've got. We're actually going to stop at example 2. Example 3 is very interesting, but it's not necessarily something that you need to know for your AP Calculus test. If you're interested in more detail about what really is going on when a series is conditionally convergent, I really highly recommend that you scan that QR code and watch this video. It's a super surprising mathematical result, which for some of you who are really interested in math, it's kind of a surprising thing. So I would recommend watching it, but just so you know, it's not something that you'll necessarily be tested on. So example 2 will be our last example that we're going to do together. Okay, so we've got the same instructions as before. determine whether each series is absolutely convergent, conditionally convergent, or divergent. And honestly, now that we know about absolute versus conditional, that's pretty characteristic that you'll want to distinguish between what kind of convergence you're deciding on. I'm going to start with absolute convergence because that's just the way that my brain works best. And so for this problem right here, I'm going to start by considering the absolute value of this series, which means I can eliminate that alternating part. And I can think about the series root n over n squared plus 1. Okay. I think I'm going to do a little direct comparison here again. I don't typically like direct comparisons, so seeing it a couple problems in a row is kind of weird. But when I'm looking at this, I'm thinking, okay, if this was just n to the 1/2 and this was n squared, I'd be able to combine those exponents, and it would become 1 over n to the 3/2. This denominator, so I'm going to rewrite this right here. This denominator is a little bit bigger than this denominator is, so that means I'm dividing by more, so what I've selected should be less than what I'm comparing it to. So let's think about this 1 over n to the 3/2 as a series. What do we know about the sum of 1 over n to the 3/2? Hopefully you're picking out that this is a convergent p-series, because p is equal to 3/2, which is greater than 1. So if our larger series converges, our smaller series should also converge. So by direct comparison test, the absolute value of -1 to the n plus 1 root n all over n squared plus 1 converges. So my original series is kind of a clunky way of writing all this, but just to be clear, we know what's going on. My handwriting is also getting worse and worse. Converges conditionally or absolutely? Absolutely, right? The absolute value of it converged, so that means it converges absolutely in its original format. Okay, one more. We've definitely got a negative piece to this one. So if we think about, I'm going to switch colors just so it's a little bit easier since I really filled up that space here. If we think about the absolute value, notice they switched over to k, so don't let that trip you up. K plus 1, 2 to the k, k squared. I think that's going to turn into a series that just loses the alternating piece. So 2 to the k over k squared. I don't think I want to do direct comparison for this one like I did before, because these aren't going to necessarily simplify to be some kind of nice power like they did over here. I'm feeling like nth term test will be a pretty easy one though. So the limit as k approaches infinity of 2 to the k over k squared. Exponential grows a lot faster than polynomial, so this limit is going to be infinity, which is not 0, and so that tells me that the absolute value of my series diverges. So if we're kind of tracking with this flowchart, the absolute value the first time converged. So that's why this decision was absolute convergence. But for part B, the absolute value diverges, and so we need to finish this up to see if it's conditionally convergent, if it meets both conditions of the alternating series test, or if it doesn't, then we'll know it's divergent for sure. And I think we already have our answer, because the first part of our alternating series test, I'm just going to write it down so we can see it, so alternating series test, is to take the limit as k approaches infinity of just the positive part of the series definition, which we have already shown is equal to infinity, which is not 0. So we failed our alternating series test right there. Our terms are not approaching 0. So that means that the series all the way back at the beginning, so since we've done some other things, I'm going to write it down just so that my reader knows what I'm talking about. So that original series diverges. It does not converge absolutely, and it does not converge conditionally. All right, everybody, I know that was a lot, and I'm really sorry that I'm not here. There's just nothing I can do about it. They haven't even selected my jury yet, so I'm still sitting in the pool waiting to hear. So hopefully I will have an update for you about the rest of the week. But hopefully this gives you enough to get in, start practicing topics 10.7, 10.8, and 10.9. Thursday is scheduled as a review day, and then you've got your long weekend, and your 10A assessment 2 is scheduled for Tuesday. So unless you hear otherwise, that's what we're on pace for. I don't want to burn too many days that we have to review for the AP test at the end of the year if we can avoid it. Email me your questions. I don't have access during the day when I'm at jury duty, but I'll do my best to check my email and get back to you in the evening. And if you have remediations that you need to take for quarter 3, try to get in and get those done. If for some reason that doesn't happen, we'll try to get them in before third quarter grades are due. We'll come up with a plan B if we need to, okay? I hope all is well. Again, send me a message if you need to. Good luck as you start working through these new tests.